All right, we're back with honors physics, free fall questions and problems. Looking at problem 7, the last problem in the set says a throne, a throne is stone. A stone is thrown vertically upward with a speed of 20 meters per second. Part A, how fast is it moving when it reaches a height of 12 meters? How long does it take it to reach that height? And why are there two answers to part B? So here we go. Let's go ahead and here's do our sketch. Here's the ground. We're going to throw a stone, right? And we're going to launch that upward with an initial speed of 20 meters per second. Going fast. As it goes up, it's going to get slower and slower until it gets to the peak. And then presumably it will fall back down. I'm going to draw this off to the side because I don't want to draw on top of myself. All right. And so the question is, how fast is it moving when it reaches a height of 12 meters? Well, thinking about this, I know that it's going to go at 20 meters per second. We know, here, I'll do some quick table of values. Well, we'll just talk about it. I know that the acceleration is negative 9.8, right? Because the only force acting is gravity. So every second, I'm going to subtract 9.8 meters per second off the speed. So I start off going fast enough to go 20 meters in a second, but I'm getting slower. After a second, I'm only going roughly 10 meters per second. But that means I'm going to have gone something in between those two, right? I start off going 20 meters a second. At the end of the first second, I'm going only 10. I've probably gone something around 15 meters up in the air, right? During that first second. So 12 meters, that's probably going to happen, within the first second of motion, right? And it's still going to be going up after that, right? So it is on its way up when we reach 12 meters. So here we go. So what I'm doing is I'm just going to, on the sketch here, we'll just say that happened here. We'll say that this is that 12 meter mark here. So we'll say this is 12 meters. And we just want to know how fast is it going when it gets there. So we're going to do this first calculation going from here to here. So let's list out our variables. This is going to be for ground to 12 meters. Okay, so I'm kind of identifying this table of values. It's for what conditions, from where to where. Let's list out our variables. A, V naught, V, displacement and time. Wonk, 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 wonk. Okay, once again, I am choosing to call upward the positive direction. I think most people would do that. So here we go. My acceleration, we know, is going to be down. That's the way gravity pulls. If up is positive, down is negative. We're going to make this negative 9.8 meters per second squared. My initial velocity, we know that it is thrown up with a speed of 20 meters per second. So going upward, make that positive. We want to know how fast it's going when it gets to 12 meters. So we're actually trying to solve for that final speed when we get to a displacement have gone up 12 meters. So there, that's the data that we know. So using these variables, A, V naught, V, delta X, probably looking for the formula that doesn't have T. The one that doesn't have T, that would be this one. I'm going to do it over here. I like working vertically, but I'm going to slide it over here for now. So we're going to use V squared is V naught squared plus 2A delta X displacement. And so you say to yourself, we are looking for the final speed. Conveniently, all I have to do is take a square root of both sides, and I will have that equation for V. So that's nice. So V is going to be the square root of that right side. V naught squared, V naught is 20, so it'll be 20 squared plus 2 times a negative 9.8 times that displacement of 12. Okay, all that under the radical. I have a negative here, so we are hoping that this term will not be greater in size than this 20 squared, because then we'd have the square root of a negative, and that would be unfortunate. But I think we're all in the clear on this one. 20 squared is going to be 400. And then this is going to be what? Negative 19.6 2 times 9.8 times 12. You see, okay, 19.6 times 12, that's going to be less than 20 times 20. 19.6 times 12, right? So it's all good. We're going to get a positive value out. Punch that in the calculator. And then I go ahead and take square root. And I got a final velocity here of 12.84, rounding, of course, meters per second. That is my speed when I get to the 12 meter mark. That's my answer for part A. Part B says, how long is required to reach this height? So how much time to get there? So now we're still going to go from here to here, so I can use the same set of data, but now it's the time we're trying to find. I could make use of this v that I solved for also if I feel confident in my answer. I've got 4 variables then looking for the 5th. I have my choice of either formula that has t. Let's go ahead and this time solve using, let's use the one that's simple. That would be v is at plus v naught. That looks like an easy one. I'm trying to solve for t, so I'll rearrange this. T would be v minus v naught over a. I can substitute in my values. My velocity at 12 meters, that was this 12.84 that I found. Is it okay that I'm rounding? Well, I'm going to cheat because I still have the exact value of my calculator. But anyway, minus v naught. My v naught was 20 meters per second, all over an acceleration of negative 9.8. You can see that 12.84 minus 20 is going to give me a negative. That's going to cancel that negative. I'll get a positive out, and life is good. So 12.84 minus 20 divided by negative 9.8 gives me a value of 14.88 seconds. Now, that is my time to get up to 12 meters. Now, it says here in part C that there should be 2 answers to part B. What's going on there? Well, what they're doing is they're thinking, if I want to solve for a time when I'm at 12 meters, that's going to happen twice. It'll happen once on the way up, and then it'll happen a little bit later on the way down. They'll be at 12 meters. I'll be 12 meters above the starting point. So technically, we can also solve for when I'm here. Okay, now how am I going to get that time? Well, when I'm over here on the way down, my acceleration will still be downward at 9.8 because of gravity. My initial velocity thrown up was still 20, but my final velocity when I'm here, it's not going to be 12.84 like it was here. It's going to be 12.84, but downward. So I could do the same calculation, but make this velocity a negative 12.84, and then I'll have the velocity here. This is making use of this fact from our 5 things to know about uniform vertical motion, that at any particular height, right, the v up equals but opposite to the v down. Okay, and that's because of the symmetry in our velocity time graph. We talked about that when we talked about problem 3. Again, if you have not watched the video on problem 3, you should do that because this information is stuff that you definitely need to know and we'll be making use of extensively next unit when we study projectile motion. So you want to know this. So getting back to this, we know that the speeds here and here, 12 meters up on your way, 12 meters above the ground on your way up and 12 meters above the ground on your way down, those speeds at those 2 points are going to be the same. So the velocity here equals the velocity here, right? And so I can just flip, just opposite sign. So I will do this same calculation again, but this time, whoops, rearrange, it's going to rearrange the same way. Sorry about that. This time when I put in my values, the difference is it's going to be a negative 12.84 meters per second. So I'm on my way down, minus 20 over negative 9.8. Okay, and when I do that calculation, negative and a negative is going to give me a bigger magnitude negative. Divided by negative 9.8 gives me a positive for time. Once again, I'm still getting a positive out for time, which makes me feel good. And I'm getting a value of 14 point, wait a second. Wait just a second. You know what I did, right? I when I did this calculation, I loused up my signs. This is actually 14.88 over here. Oops. That's not 14.88. What am I doing? What am I doing? Wait. Okay. So when I do this one, yeah, 14 seconds, that's crazy. Hang on a second. I mispunched something in my calculator when I did this. That's embarrassing, but glad I caught it. Sorry about that. Okay, so this time over here was not 14.88 seconds. The time over here actually comes out to be 0.73 seconds. That's right. Remember, we said at the start when we were thinking through the problem, we said, gosh, this is going at 20 meters per second. It's gonna take it less than a second to get 12 meters up. We needed an answer that was less than a second. I'm sorry. I feel bad that I didn't spot that right away. Not that bad, but sorry about that. Coming over here, when I do this calculation, now I do a negative 12.84 minus 20, and then divide that answer by negative 9.8. I'm going to get 3.35 seconds. Okay, I don't know where I got that 14.88 from. I punched something weird in my calculator. Sorry about that. Sorry. You've probably been wondering for the last 5 minutes what I was doing wrong. Okay, but anyway, the time I get is 3.35 seconds because that's the time for it to go all the way up to the peak and then back down to 12 meters again. So there you go. All right, so that's our answers and the logic behind this problem. All right, and that is the end of this problem set.